Okay, in this video we're going to go through Chapter 7. Chapter 7 will consist of multiple videos. So this is beginning of 7.1. So we have some definitions at the very beginning. So the first is chance experiment, and a chance experiment is a situation with more than one outcome. Okay, so our chance experiment in this situation, the very first example is Nikki's basketball free throw score, and we're doing an experiment to see what her score could be. A random variable is a quantitative variable whose value is determined by the outcome of the experiment. So the experiment is basketball shooting at the foul line, and the quantitative variable would be the score that Nikki attains through her basketball prowess. So let's go ahead and we're going to do our first analysis of Nikki's basketball free throw problem, problem A, on the next page. Okay, so I have set up the tree diagram and outcomes table and the 10 by 10 grid. So what you need to know is that here's Nikki. She's right here at the free throw line, and 60% of the time she makes that first shot. 40% of the time she does not. That's where the 0.6 and the 0.4 come from. Given this situation, if she is in the 1-on-1, she does not get a second shot if she misses the first shot. So if she gets the first shot, then she's back in the 0.6 and 0.4 world again, because now she has a 60% chance of making that next shot and a 40% chance of not making the next shot. So her outcomes are as follows. So what's the probability of her score being 2? That score is our random variable. The chance experiment is the free throw from the free throw line. Okay, so the probability of her getting 2 points is, you do a product, 0.6 times 0.6, which is 36%. The probability of her getting only 1 point is 0.6 times 0.4. Okay, so as you go down the tree, you're multiplying the numbers, the percentages, the probabilities. And so the probability of her earning only 1 point is 0.24. The probability of her earning 0 points happens when she takes that first shot and misses. And that happens 40% of the time. So the probability of 0 is going down this part of your line, and you have a 0.4%. 0.4 is your probability, which is 40%. You can model this exact same thing with a 10 by 10 grid, and sometimes this makes it a little bit easier to understand. So on the left side, I wrote first shot hits. So if the first shot hits and the second shot hits, that's going to happen 36% of the time, and 36% of the time she will have 2 points at the end of her time at the free throw line. So I have a 6 by 6 grid that represents the 36% probability. Okay, if the second shot misses, then she's only going to have 1 point. So the first shot hits, but the second shot misses. That happens 24% of the time. So I have a grid that is 4 across and 6 down. So that gives me 24, or 24%, or 0.24 as a probability of getting 1 point. So her outcome could be 1 point 24% of the time. Lastly, there are 2 ways for her to have 0 points. Actually, there's one way, but one is an action and one is a non-action. Okay, if the first shot misses, that's this grid down here. That is going to give her 0 points. Okay, then she's not going to be eligible to take the next shot, so she in effect gets 0 points there as well. All right, so that's going to happen 40% of the time, and that's why my grid is a 4 by 10. So that's the connection, and I tried to do it with the color as well, between the tree diagram, the outcomes that I've listed, and the grid. So let's go on. We're going to do another 2 of these So hopefully by the end you'll totally have the hang of it. Okay, so here's our next scenario. Again, I have a tree diagram, and the tree diagram indicates that now, starting from the top, Nikki's right here, she gets to the foul throw line, and she has one shot. She either gets it 60% of the time or misses it 40% of the time. Now, this scenario is different because this is a 2-shot free throw. So regardless of whether she makes the shot or not, she still has another shot to take. With that next shot, if she made the first one, then she may make the second one 60% of the time, or she might miss it 40% of the time. If she missed the first shot, then she has a 60-40 chance for the second shot as well. Okay, so if you want to figure out the probability that she has earned 2 points, you go down the pink, 0.6 times 0.6, and that happens 36% of the time. Okay, the 1 point option, it's greater now because she has the opportunity to take a second shot even if she missed the first shot. Okay, so this is not an and one situation. So her probability of getting 1 point is going to be 0.6 times 0.4 or 0.4 times 0.6. Either case, she's going down the green line, and that's why her probability is 0.48, because I've added up 0.24 with 0.24. Then the last option is 0 points. She gets that by going down the far side, 0.4 times 0.4, and that probability is lower because she has other options at her disposal since she has that second shot. So that probability is no longer 0.4 like it was in the previous scenario, but now it's 0.16 because I have squared 0.4. Okay, so then the chart again does the exact same thing, and it's all color-coded for you. If the first shot hits and the second shot hits, she's in the pink. That's why there's all these 2s, and the 2s take up 36% of this 10 by 10 grid. If she makes the first shot but misses the second shot, she can get 1 point that way. She can also get 1 point by missing the first shot but hitting the second shot. And then she can get 0 points by missing both the first and the second shot. And you can see it's all color-coded, so hopefully this is starting to kick in. We have one more scenario, and we're going to change our success rate. We're going to have another Nikki with an I this time, and she has an 80% free throw success rate, and she's going to have a 2-shot free throw situation. So we're going to do that on our next page. Okay, so here's our third scenario. So this Nikki is an 80-20 success versus not success shooter, and you can see that her tree diagram reflects that change. Her probabilities reflect the change, as does the 10 by 10 grid. So everything is labeled, everything is color-coded. You should be able to figure that out and be comfortable doing this after having seen it twice before and without me explaining it in as great detail the third time. So it's kind of a nice way to present things. It's very visual. Middle school, even some smarter or higher up elementary school students can appreciate this and could understand this scenario, and it's kind of neat to use all the different color to make it kind of jump out at you. Okay, this next little section is from a problem within the text, and it talks about a fair game. So by definition, a game is fair, and this is a game of chance, so not a game of technique or a game like Jeopardy of knowledge. So a game of chance is considered fair if every player playing has an equal chance of winning. So these are the rules and how people score. So you're rolling 2 different die at the same time, and then you sum the die, and depending on the sum, either player A, B, or C gets points. So if player A is playing, he or she will get 1 point if the 2 die sum to 1, 2, 3, or 4. So think about this. 2 die are never going to sum to 1, so that's already out. Okay, they'll sum to 2 exactly 1 time. They'll sum to 3 2 times more. They'll sum to 4 1, 2, 3 times. So out of the 36 possibilities for sums, which we calculated or tabulated in this little chart, player A only has 6 opportunities out of the 36, so right here, to actually get a point. Okay, so I am enumerating that by this probability chart. So the probability chart pulls each of the sums and tells how often that sum appears. So you can see for the orange player right here, that sum is indeed going to be 3 plus 2 plus 1, 6 out of the 36 times. So look at the green player. The green player gets a point, and I'll change this color a little bit. The green player gets a point if the sum is 5, 6, 7, or 8. So check out all the different ways this player can get sums. Look, 7 is the most frequently added sum, and you can see that there's a ton of values here. So if you add them up, as I have, there's 4 for 5, 5 for 6, 6 for 7, and 5 for 8. So if you sum those up, B has 20 chances out of the 36 to get a point. Going on to C, we'll change this one more time and make it light pink. Okay, so for player C gets a point if, and I missed some of the 8s over here, if you have 9, 10, 11, and 12. So just as the visual, you can see that you're not really getting a whole lot of points here, right? So if this is pink, well, I should probably do it. If this is light blue, so we'll make it a light blue. So the light blue is C, and C gets points over here. Okay, I'm going to do this. I'm going to undo it. So that's all the places that C will get points. Okay, and where will the green get points? All in here, and look how many points are available. Okay, so that's all your greens. You can see that's the largest part of the pie here. Okay, and then if you go back to the orange, we'll make that a light color. Here are your orange points, all in here. All right, so you can kind of divvy it up and see. And it looks to me like the orange player has the least amount of chance of winning, followed by the blue player, followed by the green player. So I'll get rid of all of this so you can see the chart again. So the probability chart helps me to see it. The dice chart helps me to add up each roll, and I can analyze this by putting together this little table as well. Okay, so the bottom line is this is not a fair game of chance, because not every player, the 3 players that are playing, will not have the same chance of winning. Or I should say the same chance of getting a point. Okay, 7.2 addresses the mean of a random variable, which is also known as, aka, the expected value, and that's going to be the mu. So that's your average value. Okay, so that means that if you figure out on average how many points Nikki's going to earn each time at the free throw line, that would be the mean of the random variable. Okay, so let's look back at that situation. So look back on her this should be 1 and 1, not 1 on 1, 1 and 1 situation. So for 100 outcomes, she has 20 outcomes with 0 points. Okay, so 40 outcomes with 0 points, so that's 0.4 times 0 points. And you have 0.24 times 1 point, and you have 0.36 times the 2 points. Okay, what total number of points would you expect Nikki to score if she's taking 100 trips? So if she's going to have 100 trips, all of these percentages now become whole numbers. So 40 times 0, so I would say 40 times 0 plus 24 times she's going to get 1 plus 36 times she's going to get 2. So if you add those up, she has a total points of 96. So what is her average, aka mean? What's the average number of points per trip to the foul shooting line? Well, if she's going to go up 100 times and she gets an average of 96 per trip, then her expected value for the situation is almost 1 point, okay, 0.96 of a point. All right, so expected value or mean of a random variable, I got this mu by doing this calculation. So what did I do? I took each value times its probability, but because I'm going to do it 100 times, I multiplied the probability by 100. So x1 was 0. Okay, the probability of 0 is 0.4 out of 100 if I'm going to go 100 times. Or actually, it's 40 out of 100. If you go 100 times, the probability is 40. Okay, x2, if it's the chance of getting 1 point, the probability of that is 24 out of 100. If I go 100 times, it's 24. Plus, if I had 2 points, the probability of that is 36 out of 100. If I go 100 times, I have 36. So my expected score, my expected points will equal 96. Okay? So 96 total points. So let's go back for a second. If I just want the mu, okay, so I don't want the total points, I want the mu, keep your decimals in here. Okay, if I keep my decimals in there, my average is going to be 0.96, and that's really what I want. If I say I'm going to go there 100 times, then you can say, okay, as she's leaving the court, she would have possibly earned 96 points of those 100 times to the foul trip line. Okay, so that's how that works. Can we do the other averages the same way? Yes, we can. So you can take each of those. So, for example, Nikki's weighted average for the 2-shot. So why don't we go through that? So I'll erase what I have here. Well, why don't I say, I'll keep it here. So this is Nikki 1. Her expected average is 0.6. So that's going to be the mu. We'll have a little table going. Okay, so let me erase what I wrote here, and let's do Nikki 2. Okay, and we'll change that color as well. So this will be Nikki 2, and Nikki 2's weighted average is going to be, let's see, she has, for getting 2 points, so the 2 points is going to be an average of 0.36. 1 point, so 1 point has a probability of 0.48, and 0 points has a probability of 0.16. Okay, so we're going to multiply those together, and what we should be getting is, let's see, let me do it and then turn it back on. Okay, yes, so you should have an average of 1.20 here. So Nikki, when she has the opportunity to have 2 shots, she has a higher average, which is consistent. Okay, what about our other Nikki? We'll change colors, and we'll do the other Nikki because she's a little bit of a better shot. So when she's a 2-shot situation, so how do her numbers change? So we'll erase this again, and we'll do her in purple. Okay, so the probability of getting 2 points. So 2 points had a probability of 0.64. 1 point had a probability of 0.16. And 0 points had a probability of 0.04. So when I add those together, I am getting an expected average of 1.60. So you can see, because she is a better shot, she is having a higher chance of scoring. She leaves with an average of 1.6. Okay, so that's the 7-2 on this page. Let's go to the next page, which is a lawn mowing problem, similar to the basketball problems, but with a little different spin on it. Before we move on, I'm just going to make one little correction down here. This, if you had looked back, was 0.32, and now my sum is correct. So that adds up to 1.6. So we're all good. Okay, let's go on to the next page. Okay, so this is the next problem. It also has a pair of die in the problem. So let's read this. It says, Mr. Fajita hires Tasa to mow his lawn for the summer. When Tasa asks him how much he will pay her, he offers her two options. The first option, he says, I'll pay you $10 every time you mow. So this is option one. No variation, just $10 each time she comes. Option two, however, is each time Tasa mows the lawn, she will roll a pair of number cubes or dice. If the sum on the cubes is 7, so here's our little cube chart, so we can see that 6 times out of 36, or 1/6 of the time, it is, she would roll a 7. So 1/6 of the time, she will get paid $30. If the sum, however, is not 70, so look at all the other sums she could have, that would be 5/6 of the time, he's going to pay her only $3. So what is her expected payment? Remember how we did that? We said the probability times the payment, or times the score for the basketball situation. So plus the second set of probabilities. So we're going to sum them up. Okay, so this was x1 times the probability of x1 plus x2 times the probability of x2. That's what we're doing from the previous example. So option 2 gives her $750 as her expected payment. So given those two scenarios, her best bet is to go with the straight option 1, because she'll always get $10, and that's a better expected payment than is the $750. Okay, we're going to go on the next page, because we do another little variation of that, where we work with option 2, but call it option 2A and 2B. So let's do that next. Okay, so I've written down option 1's result and options 2 results. Now let's look at option 2A. So Mr. Fajita is going to pay her $30 if she rolls a sum of 7. Okay, so that, how often does that happen? So that's going to be $30 times, remember we said it was 1/6. Now he wants to know how much should he pay her if she does not roll a 7. So it's some number, we'll call it x. That's going to happen 5/6 of the time. And he wants her expected mean payment to be $10. So you see how now you're going to solve for what this payment's going to be? So let's go ahead and do that. Well, first off, we can make our numbers simpler. 30 times 1/6 is 5. So you can make this 5. So now you have 10 equals $5 plus some other x times 5/6. So subtract $5 from each side, and you get 5 equals 5/6 times x. Multiply both sides by 6/5. 6/5. So it looks to me like it should be $6 every time she does not roll a 7. And that will get her expected mean to be $10. So in this case, x should be $6. So that's option 2A. So let's look at option 2B. 2B says he's going to pay her $3 if she does not roll a 7. Okay, so if she does not roll a 7, that x that we didn't have before is going to be 3. So 3 times 5/6 of the time. How much should he pay her if she does roll a 7? So now our x is where the 30 was, times 1/6, and he still wants her expected mean to be $10. Okay, so let's look at this. Let's see how we want to do this. So this is 15, 3 times 5/6. Well, actually it's 5 over 2 when you reduce, right? So 5 over 2. So 10 minus 5 over 2 equals x times 1/6. So multiply both sides by 6, and I'm going to do it over here. 6 times 10 is 60, minus 6 times 5 is 30, divided by 2 is 15. So that means in the second case, you would have the option B to get paid $45 if you roll a 7. So in that way, her expected payment is going to be $10. Okay, so interesting little spin on things. Again, using dice, very handy for kids to be able to use, and you can play around with those numbers. So let's move on now, and we're going to talk about 7.3, which is variance and standard deviation. Okay, in 7.3, we're going to start talking about variance and standard deviation. So we're going to look at option 2A of the TASA lawn mowing problem, not law mowing. So it's presented here. So let's see. If she was getting paid $30, right, that she got that when she rolled 7. So the probability of the 30 was 1/6. The probability of the 6, because remember, Mr. Fajita wanted to have her average expected income to be $10 for every lawn mowing. Okay, so for 6, the probability of that was going to be 5/6. So what's the deviation? The deviation is around the mean. So if your x is 30 minus the mean, which we said was 10, that deviation is 20. Okay? This deviation is greater, isn't it? So let me just redo that. So this is going to be 6 minus 10, and you're going below. So the deviation of the 30 from the 10 is greater and it's positive because it's above the expected income. The deviation of the 6 value is below by 4. Okay, so to go from deviation to variance, you square it. So squaring the 20 gives you 400. Squaring the -4 gives you positive 16. All right, so if you are 4 units either up or down from the mean, your variance is going to be 16. If you are 20 units either up or down from the mean, your variance is going to be 400 since you have squared the terms. Okay, so when we're working with these weighted averages, in order to determine variance, this is how we're going to do it. So we're going to take this squared value and we're going to multiply it by the probability. All right, so what am I going to get? And we're going to sum them all up. So in the first situation, we have 400 times 1/6, and then plus 16 times 5/6. And if you were to do the math, what you should be getting is that your variance is 80. Okay, so standard deviation would be the square root of that. So standard deviation would be radical 80. Okay, and you can do the math for that. Now, the whole reason why we're doing this is because we want to work on z-scores. Okay, z-scores are very typically used in a stats class. So how do you get a z-score? So the z-score is x minus the average over the standard deviation. So let's do that on the next page. Okay, so let's use the standard deviation, which was radical 80, to get our z-scores when the x is 30 and again when it's 6. So this is what I've done here and here, and you can see that when your average is below your actual value, your z-score is positive. When your average is below, is lower than the value, then, when your average is higher than the actual value, your z-score is going to be negative. Okay, and we're going to play around with z-scores a lot in this section. So the next thing we're going to do is work on TASA's earnings using option 2B. And we're going to employ the calculator now so that we have another way to calculate these, not always having to do it by hand. Okay, so what we're going to do now is we're going to work on data from 2B. So in 2B, remember that your y was 3 and 45, and the probability of the 3 was 5/6, and the probability of the 45 was 1/6. We are looking for standard deviation. So what we're going to do is we're going to go to stats, and we're going to put the 45 and the 3 in the L1, and the 1/6 and the 5/6 in the L2. When you put 1/6 and then 5/6, it's going to turn into decimals. Don't worry about that. It's all fine. Okay, we're going to then run one variable stats, but you're going to say when you do that, so if you go stats, stats, calc, one variable stats, it's going to ask you where is your list. Well, your list is in your L1. Then it says frequency. When you have your probability, that is your frequency. So tell it that your frequency list is in your L2. And then you can hit calculate. And if you look, you will see that your standard deviation is given to you, your sigma, and if you round to the nearest tenth, it is 15.7. So sigma equals 15.7. So go ahead and get your two z-scores. So what's the z-score when the x is 45? And then what's the z-score when the x is 3? So go ahead and put that in your calculator, and you can calculate it out knowing that, remember from the previous page, z equals x minus mu. Mu is still going to be 10 in this situation, over standard deviation, which you're going to use is 15.7. So you should be getting that the z-score for 45 is 2.23, so that's above the average, which makes sense. And the z-score for 3 is negative 0.45, which is below the average, which makes sense as well since the average is 10 and the value was 3. So that gives you a little insight into using your calculator to get standard deviation and also in doing your z-scores. So we're going to stop this video here.